This is the presentation for the paper Safe Reinforcement Learning for Autonomous Lane Changing Using Set-Based Prediction, published at ITSC 2020. The authors of the paper are Hanna Krasowski, Zhao Wang, and Matthias Althoff. For safety-critical tasks like autonomous driving, we have to guarantee that the behavior of the controller is safe. However, the interaction between the environment and the agent is usually not explicitly specified, so direct verification is challenging. One possibility to estimate if safety criteria are met could be to test if the reinforcement learning agent behaves in a safe manner. But for complex environments like autonomous driving, testing is not a feasible option, because there are infinitely many possible situations that could occur. If safety guarantees are necessary during training and deployment, the classical reinforcement learning has to be adapted towards safe reinforcement learning where the exploration process is guided. So only safe actions could be performed by the agent. In this work, we propose an approach which constrains the actions of the agent to only safe actions during learning and deployment. First, let's have a look at the general reinforcement learning problem. The agents choose an action upon the information provided through the current state. This action acts on the environment generates the next state and the reward, which indicates how beneficial the last action was for reaching the goal. To extend this framework to safe reinforcement learning, we add a safety layer that outputs the safe action mask, which indicates the safe actions. To generate this prediction, the safety layer receives the states of the surrounding vehicles and the ego vehicle. For determining which actions are safe and which not, we use the set-based prediction tool Spot to predict reachable occupancies for other vehicles and a low-level trajectory planner for the ego vehicle prediction. If there's no safe action identified, we apply a failsafe plan in the study Approvably Safe ACC. So how did we model the problem exactly? A schematic highway traffic scenario is depicted here. The task is to reach the goal area from an initial state on a highway safely. Safety in this context means that the agent is not allowed to collide with others and should not violate the safe distances which have to be regarded. This is usually the safe distance to the leading vehicle, but during a lane change also to the following vehicle on the target lane. The reward enforces learning this task and consists of 5 terms. The first term is a sparse reward given when the goal is actually reached. The second term is given when the agent is driving in the same lane as the goal is located. And the third reward encourages the agent to drive closer to the goal. The other 2 terms penalize the agent if it collides with other vehicles or violates the safe distances which have to be regarded. Now, what actions can the agent choose to fulfill this task and optimize its behavior according to the reward function? In general, the agent has 3 discrete options: to change the lane to the right or left and driving straight ahead. If the agent is already in the rightmost lane, the action for changing to the right would be excluded. The fourth action is the failsafe plan, which is only possible to choose when the other 3 actions are unsafe. The agent observes the environment through the state space. This state space provides information about the surrounding vehicles during their relative velocity and longitudinal distance. We consider only vehicles that are close enough to matter for the agent's decision and thus introduce a sensing range of 150 meters. In this area, we consider 6 positions for the 3 possible lanes relative to the ego vehicle, and in each of these lanes, the closest leading and following vehicle to the ego vehicle. So in this figure, vehicle LF stands for the following vehicle in the left lane. Further, the state space includes the lateral and longitudinal information to the goal and the absolute acceleration and velocity of the ego vehicle. Predicting which actions are safe and which are not is essential to our approach. Thus, we mask all actions that are regarded as unsafe, so the agent can only choose safe actions. To generate the mask, we first check if a lane change is conducted currently. Then we mask all actions except the corresponding lane change action to avoid that the lane change is aborted before it's finished. Otherwise, we have to predict which actions are safe and can be conducted. If at least one of the 3 high-level actions are identified as safe, the agent can choose among the safe ones. If no action is safe, we switch to the failsafe plan. So in more detail, how do we identify the safe actions? First, we detect only the surrounding vehicles which really affect the planning of the ego vehicle. Here the orange rectangle. For those surrounding vehicles, we predict their future occupancies with SPOT, our set-based prediction tool. The orange areas schematically show the predicted occupancies. Then we use the low-level planner to transform the high-level actions to feasible trajectories and enlarge them with the shape of the ego vehicle to get occupancies for the ego vehicle. The generated trajectories consist of a first part, here in blue, according to the high-level action, and a braking trajectory, here in gray, to ensure that the agent can always reach an invariably safe state. The blue part will be conducted if the agent selects this action, but the gray part is only used for checking safety. Now we can compare the ego vehicle trajectories with the predicted occupancy areas of the surrounding vehicles for each time step, and determine which trajectories intersect with occupancy areas and thus are unsafe. If we cannot find any safe action among these 3 actions, we switch to our failsafe plan. Here we utilize the provably safe adaptive cruise controller. To actually train the agent, we have to choose a learning algorithm. For that, we conducted preliminary experiments with 3 different state-of-the-art algorithms for discrete action spaces. Proximal policy optimization, PPO, is an algorithm which directly optimizes the policy. Deep Q networks, DQN, where the optimal policy is inferred from the learned Q value and which is more sample efficient. And actor-critic with experience replay, ACER, which combines ideas from PPO and DQN. The preliminary experiments showed that PPO has the highest goal-reaching frequency and also the lowest computation time. Thus, we selected PPO, but in order to ensure that only safe actions are selected, the algorithm has to be constrained to only safe actions. In order to evaluate our approach, we use 2 different types of policy networks to train the agent: a regular multi-layer perceptron, MLP, and a long short-term memory network, LSTM. The MLP is the standard network, and recurrent networks like LSTMs are suited for sequential tasks like ours. Further, we compare 2 training modes for these 2 networks. The non-safe mode, which is classical reinforcement learning without a safety layer, where the agent can choose among all actions, and the safe mode, where the safety layer is integrated and only safe actions can be selected. Thus, in total, we compare 4 types of agents. We train the agents on real traffic data and use the HIDI dataset, which was recorded with a drone above German highways for 3-lane and 2-lane roads. One example scenario of this dataset is displayed here. The initial state and goal area are generated from a trajectory of a real human driver. We used 5 hours of traffic data in total, while the time discretization of the dataset is 40 milliseconds. We split the dataset in 80% training and 20% test set. The training results show that our approach works, as the safe agents do not cause collisions and do not violate the safe distance to other vehicles. In addition, the safe agents need less training steps to converge and achieve high rewards from the beginning, as visible from the reward figure on the left-hand side. These high rewards are due to the fact that the safe agents just explore the safe action space. The large negative peaks for the non-safe agents result from situations where the ego vehicle almost collides with the leading vehicle, and thus the penalty for safe distance violation is very high. Comparing the 2 different policy networks, we cannot identify a significant difference between them. When testing the trained agents on the test dataset, the safely trained agents still do not cause collisions, thus the approach is safe for learning and deployment. The non-safe agents reach the goal more often, and for the safe agents, the LSTM agent performs better than the MLP agent. In addition, we check with multiple metrics if the trained agents behave similar to the human driver from which we generated the initial state and goal area. The plot on the left-hand side visualizes the mean velocity as example metric. The percentile curves for the agents and the human driver are very similar, thus the learned policies seem realistic. Here are two test scenarios animated for the LSTM agents. For congested traffic, the safe agents sometimes cannot reach the goal as in the upper scenario, but the safe agent's behavior remains safe in contrast to the non-safe agents, which violate the safe distance as in the upper scenario. For less congested scenarios, like the lower one, both agents perform similar and reach the goal. In conclusion, we developed an approach which is safe during learning and deployment and thus is applicable to safety critical tasks like autonomous driving. Thank you for listening.